Our next topic is going to deal with volumes and surface areas of three-dimensional objects. Okay, so instead of two-dimensional polygons, we're going to get into three-dimensional things. And just kind of as a basic shape is our rectangular solid and our right circular cylinder, but we'll talk about both of these. And we're going to talk about volume first. With a rectangular solid, basically it's a three-dimensional object that is completely made up of rectangles. The edges or the sides of it are rectangles, and those rectangles are at 90-degree angles to each other. Okay, and so a rectangular solid, if you were to think about it like I kind of think about so like a cereal box would be a great example of a rectangular solid. And any rectangular solid is going to have three important dimensions to it: a height, a length, and a width. Okay, the height obviously is the vertical distance, vertical dimension, and then you have what we call the base of this rectangular object or rectangular solid. And the base here, I kind of dashed in the edges that are behind the front surface there. And of course, we'll run another one down this way. All right, so that should give you all the different surfaces. Now there are 6 rectangular surfaces put together on this rectangular solid. One in the front, one in the back, top, bottom, left, and right. So that's 6 total. And so you can imagine, hopefully, that if you could fill this up with little cubes. Cubes are rectangular solids that all have the same dimension, all 3. They're 1 by 1 by 1, whatever we're measuring in, feet, inches, meters, whatever it is. And you could put these little cubes in here, and you could lay them in, and however big the base area is, that gives you a set amount per layer of cubes, and then the height gives you multiple layers stacked on top of each other. And if you were to just take your base layer and multiply by the height, that would give you the total number of cubes within the surface, or within the solid. Okay, and so to find this volume, you take the base area, which we'll have length and width on the base area, and the base area we'll often call big B. It's kind of like big A for area, but it's B for base area. Okay, and so the volume of this object is the length times the width times the height, or you could also call it the base area times the height. Okay, and again, that base area gives you the number of 1 cubic unit cubes, the number of cubes, individual cubes per layer, and then the H gives you the number of layers that you stack high, and then the volume is the total number of cubes in that solid. Okay. All right, so that's just a general formula for any rectangular solid. What's kind of neat about that is that if you imagine tipping that rectangular solid in any dimension so that the rectangles are no longer at 90-degree angles to each other, but they're tilted, the volume formula doesn't change, which is kind of an interesting fact. It's kind of like taking a deck of cards. If you've ever seen a deck of cards stacked up, that's a very short rectangular solid. And if you just kind of push the deck over, just kind of push the cards so that the edge is on a diagonal instead, they kind of just shift over but remain stacked, and what ends up happening is the total volume is the same whether they're upright or tilted. The total volume doesn't change. And so what's fascinating is that each card in the deck is like a cross section of that solid, and so long as the cross sections are consistent, they're the same size. So like in this rectangular solid, every cross section is exactly the same as the base, then you will have this formula where the base area times the height gives you the volume, okay? Similar for a right circular cylinder. Okay, a right circular cylinder is basically so it's like a can of beans or a can of tomatoes. It's or a can of soup. You have a circle and a surface, a vertical surface. Didn't quite turn out as nice as I wanted it to. There you go. And this vertical surface that kind of surrounds the can or the cylinder shape. And I called it a right circular cylinder, which basically means the cross sections are circles and the vertical surface there is at a 90-degree angle to that base circle, those cross sections. And again, what happens is to find the volume of this thing, if this has let's see, say those circles have a radius of r, then, and we'll throw a height of h in here as well, then the volume is similar to the rectangular solid. You have a base area that gives you sort of one layer of cubes, and then you stack them high equal to h layers. And so the volume will be the base area, call that the base, multiplied by h. Well, what's the area of a circle? Well, we learned that before. It's pi r squared, right? So this is equivalent to pi times the radius squared times h, the volume of a right circular cylinder. And so in both cases, with the rectangular solid and the cylinder, the base area times the height will give you the volume of those objects. Now, what's also interesting is that there are other geometrical shapes that are portions of these, namely the pyramid and the cone. Right, there are many other rectangular solids. We're just going to get into a couple of basic ones. The pyramid is what you would get if you took this a rectangular base and built triangular sides out of it. Okay, so you'd have, I don't know if I can draw this real well, but you have that curved. I didn't want that to curve. There, and right there, and then down to the front, down to the front. That's not too bad. Anyway, that green object that's dashed on the inside is a pyramid. A pyramid basically has a rectangular base and triangular vertical sides that all meet at a common vertex. Okay, so the pyramid, maybe I can draw a little bit better one here. Oops, not a good angle. We'll take one out here to the side. And I should probably dash this. Okay, and then going up, we need a common vertical vertex here. Oops. All of my edges on this side are going to be solid. That edge will be solid. And then there's going to be one edge behind that is dashed right there. Okay, so there's my pyramid. And then essentially you have this base area again, but this time the cross sections are not consistent. They shrink as you go up. You know, they're still going to be rectangular in shape, but they shrink as you go up to that point. And so it's going to be a portion of this volume. So you're going to have this base area times height kind of relationship with some sort of scaling factor that cuts this down so that we're not filling up the whole volume of the rectangular solid to give you the pyramid. We're not going to do that. And so for a pyramid, the scaling factor is 1/3. Now there's some reasons for that. There's a derivation which I'm not going to get into, but the volume for the pyramid is essentially 1/3 the base area times the height, and the height is then this vertical distance down to the center of the base from the vertex. Okay, so that's your height h. All right, so that will give you the dimensions there for the volume. And of course you could replace the B with an L and a W if you wanted to, because that is a rectangular base. So the volume is 1/3 length times width times height. Okay, that would also work. And what's interesting is if you do sort of a similar derivation on the cylinder, we get a cone. You can take this middle point of the upper circle and drop an edge down to the base circle there, and you get this conical shape, right? If you allow that to be, circular cross sections. It's kind of like a waffle cone for eating ice cream, right? Upside down apparently. And the volume is, again, of this cone. So for a cone, let's go ahead and I'll redraw this. So you get a single cone there. The base area multiplied by the height, h, from the center of the base circle up to that vertex. Okay, so the volume here is going to be, again, the base area times the height. But no, it's not. It's 1/3 of that. Just like this one is 1/3, that one is also 1/3. Sorry. So it's actually 1/3 base area times the height. And that base area is, of course, pi r squared still. And so we really could write this as 1/3 pi r squared h. That's the volume of a cone, all right? Now, don't worry, when it comes to your test, I'll be giving you these volume formulas. I'm not going to expect you to memorize. Well, actually, I would not give you the rectangular solid formula, but I do plan to give you the formulas for the pyramid, the circular cylinder, and the cone. Okay. All right, so anyway, those are your volume formulas, and so you can use those. If I had maybe I had a deck of cards. I don't know what the size of a deck of cards exactly is, but let's say it's like 1 inch by 3 inches by 4 inches or something like that. Okay, and that's just your little flat deck of cards, right? And so the volume of that is just the product of those three numbers, 1 times 3 times 4, which is 12 cubic inches. Okay, you just multiply the three dimensions, the three values together. For any rectangular solid, you can do that. If I wanted a cereal box, for instance, let's say this is more like a cereal box, and let's go with like, maybe it's 2 inches, the width is 2 inches, the length here is maybe more like 8 inches, and the height maybe more like 12 inches. Then in that case, the volume of that solid, and I'll put it up here, the volume would be length times width times height, right? Length times width is your base area, 8 times 2 times 12 height, which is, 24 times 8 is 160 plus 24, 184. Could I be mistaken on that potentially, but I think that's right. 144. No. I don't know, does that seem right? That seems a little bit off. Let me just double check that. 8 times 2 times, what did I say, 12? 192. How did I get 184 out of that? I'm not sure what was going on in my head there. 192. Yeah. I didn't think it should end in a 4, that's why I was bothered by that. Cubic inches. So you got 192 cubic inches in that object there. I don't know what I was thinking on that one. Okay, anyway, I'm not going to edit that out. You can see me make mistakes every once in a while. Okay, so there's our rectangular solid. If I had a pyramid, let's say I threw some numbers in here. If our if our length of this pyramid was 5 feet and the width was, I don't know, 4 feet and the height was 6 feet. So maybe it's a 6 foot tall pyramid with a 5 by 4 rectangular base. Then the volume of that would be 1/3 length times width times height, 5 times 4 times 6. Whenever I have these fractions, if I can simplify, I usually do right away. It keeps my numbers smaller. So 3 goes into 6 twice, right? So I get rid of that. And then I just have 5 times 4, which is 20, times 2, which is 40. So my volume here is 40 cubic feet. It means I could fit 40 1 by 1 by 1 foot cubes in that pyramid with those dimensions. Okay. And of course, if we want to go to the circular cylinders, we can do that as well. Let's say, for instance, you have maybe you're a circle, base circle with a radius of 5 inches and a height of, I don't know, maybe another 6 inches. Throw that in there. Okay, and then in that case, the volume is going to be your base area, which is pi r squared, and then multiplied by the h, which is the 6. So r squared is 25, so that's pi times 25 times a height of 6. And I just have to calculate, well actually, I'd probably do the 25 times 6, ignore the pi for a moment. That's 150. So that's pi times 150. And then I'll just estimate this at 3.14. So you have, I'll put it up here on the side, 3.14 times, I'll go 15 and then I'll tack on the extra 0. So in fact, I'll get rid of the decimal 2 for a moment. So I go 5 times 4, 20, 5, 6, 7, 15. I'm trying to do this without a calculator, even though I have one sitting right there. 4, 1, 3. Add those up. 0, 11, 5, 6, 7, 4. I do need an extra 0 on the 150, so I put a 0 in, and then I need 2 decimal places, so I got 471. Right? Yes, 471. It came out nicely. Look at that. Cool. 471 cubic inches. Okay. So in the right circular cylinder with those dimensions, you'd be able to fit 471 1 by 1 by 1 cubes in it. And finally, with a cone, let's just say for a moment that all these dimensions are the same. Let's just put a cone inside that cylinder there. So we've got R is 5 inches again, and H is 6 inches. Well, essentially, the volume of that is going to be 1/3 of the original cylinder. So the volume is going to be 1/3 times that 471, which does work out nicely. 471 is divisible by 3 because the sum of its sum of its digits is 12. So what would we get? 3 goes into 4 once, into 17 5 times, so it's 150, 21, 7, 157 cubic inches. Double checking. 471 divided by 3. 157. Perfect. There it is. Okay, so all these volumes can be found using the 4 formulas up here. But again, the general principle is you take the base area times the height. That gives you your sort of your basic solids. And then if you're going to cut chunks out of them, like you do for the pyramid or for the cone, then you have some sort of multiplying factor to scale that down, which in both cases ends up being a 1/3 factor to do that, which essentially means you could fit 3 of these pyramids in the same size rectangular solid. You could fit 3 of these cones in the same size can. Okay, so if you had a can full of ice cream, it would take 3 ice cream cones, waffle cones, to fill that up to the top, right? You wouldn't want any extra ice cream hanging off the top. But anyway, that would work. So those are your formulas for your area and how you can use them. I'm sorry, for your volume. Formulas for your volume and how you can use them.